I want to show you how I managed to almost double the CPU speed of my 10-year-old laptop without overclocking. I did it with a new air cooling system. And if you're trying to speed up your CPU, your PC or your laptop by overclocking the CPU, why don't you try this first? And then try overclocking your CPU if you need it. That means if your computer is still not fast enough. Doubling the speed of your computer will depend on your room temperature. If it is too hot or too cold, you may not get the performance improvement that you're looking for. Furthermore, if your computer is an old computer, go get it serviced first. Make sure you don't have any dried thermal paste and replace it with fresh thermal paste. And then clean up all the dust that is blocking the airflow. I did it to my old 10-year-old Samsung and I got about 10-20% improvement in performance just servicing it, and that is really good. I will do another video on how to simplify and improve this cooling technique because I am trying to source all the parts and trying to look out for another desktop PC. There are a few more ideas that I'd like you to understand so that you can implement something similar to what I've done on your PC or laptops. Let me explain the physics behind thermal conductivity, the insulation problem, and the air cooling techniques I've developed over the years. Then you will have a better understanding of how this air cooling system works. Firstly, let me explain. There are three ways of heat transfer, that is radiation, conduction, and convection. The main systems used in computers is conduction and through thermal paste and convection by air or water cooling. You must understand that cooling depends on a temperature differential for heat to be transferred. The more conductive the material is, the more heat be transferred out quickly. If the temperature differential is great, then more heat will be transferred also. The greater the temperature differential between the outside of the package and internally on the silicon die, the more heat will be transferred out of the package. I became interested in chip cooling about 35 years ago when I was upgrading ovens while working in the semiconductor industry. I discovered that the temperature sensors that we were using had a 5-degree error, 5 degrees centigrade error, which is 9 degrees Fahrenheit, when measuring oven temperatures at 125 degrees centigrade or Celsius, or which is 257 degrees Fahrenheit. And so after some experimenting, the temperature sensors that I was using to measure oven temperatures was the AD590. And what I noticed was that thermocouples didn't give this error, only this sensor. And that was because it was a silicon die wafer that was mounted inside a metal container. But the internal contents of the container was some paste creamy stuff to protect, I guess, the silicon die from electrical connection to the outside casing. So even though the sensor was exposed to oven temperatures of 125 degrees Celsius, the die inside was electrically connected to by some cables to the temperature sensor electronic board. And what was happening was the heat on the die itself was being conducted out through the cables, which were at room temperature. So that is the reason why that even though the oven temperature was 125 degrees, the die was seeing a lower temperature because it was losing heat through its leads, through the cables attached to the leads. And looking back, I thought that would be a very good idea to try to implement some cooling system for the PC and laptop CPUs. As you can see from the above drawing, the chip packaging is normally made of plastic or epoxy or ceramic or some other insulating material. That means cooling through the packaging will be inefficient and probably slow. If you examine the metallic part of the chip construction, it consists of the leads and the lead frame and wire bonding attached to the tracks on the silicon die. Those parts would form good heat conductors. So, a good alternative is to try to cool the die through the leads. In this example, we can observe that a fan blowing onto the top of the package will not be that effective, as it will be cooling the package directly, and in so doing indirectly cooling the die. Whereas if we blow the fan at the leads of the chip, we will be directly cooling the die inside quickly. Let me explain the terms used. The motherboard has most of all the components on one side, and this is called the component side of the motherboard. The underside of the motherboard is mostly solder of pins sticking out, and this is called the solder side of the motherboard. There is one exception to this, and that is the Taiwanese manufacturers of motherboards call the solder side the back side of the motherboard, because they do have some surface mount chips there too. It was because I was running these experiments on my old Samsung laptop. I learned a lot about laptop design, and I'm going to explain them as we go along in the video. I ran all my tests on the Intel i7 2630QM CPU. Initially, I thought I would not be able to test for overclocking because this CPU could not do any overclocking at all. Fortunately, as I ran my experiments, I realized that it was an excellent CPU to test the airflow techniques, as it could not be overclocked. That means any CPU speed improvement I saw was due to the airflow and thermal considerations. Let me show you why airflow in the laptop is very important. My old Samsung laptop was performing around 480 to 550 Cinebench R20 rating. My new Acer Nitro 5 laptop used to perform at 2200 or 2300 ranking when I first bought it. Unfortunately, the NitroSense app stopped working long time ago. It was the app that controlled fan speed. Today, there is only a fixed fan speed on this Nitro 5 laptop. So from the chart, you can observe that on a warm day, the Acer Nitro 5 laptop can begin with a Cinebench R20 rating of 1930. But as the CPU warms up, the ranking drops to about 1600. On a cool day, the ranking begins from a lower value of 1210, and as the CPU warms up, its speeds improves to 1600. From here, we can deduce that for laptop CPUs, a room temperature that is too low or too high will slow them down. They will take some time to adjust to an operational temperature. This may be much slower than expected if the cooling fan is not working properly. So you can understand why sometimes the cooling fan will not turn on, because the room temperature is too low. At higher room temperatures, if the fan is not fast enough, you will end up with a slower laptop. There was additional information I learned from running all these experiments. It's amazing how well designed CPUs are. You can see that the performance jumps in steps or quantums. Why? Let me see how to explain that. This is the performance of my 10-year-old Samsung laptop, the i7 one. I had removed the casing, the screen, and the keyboard. It lay exposed to room airflow and was fitted with an external remote keyboard, and the HDMI connector was connected up to my TV screen. I ran the Cinebench R20 program continuously, and as the program ran, the CPU warmed up. There was no additional cooling airflow, only the fan attached to the CPU with the copper heat sinks, which is the standard laptop design. You can observe that as the CPU warms up, the performance drops in steps. Is this because the internal voltage and the clocking frequency are adjusted in steps? It is about 13.4% change per step. Does this mean that the CPU could have slowed to 423? And if pushed, could it have performed at a Cinebench R20 ranking of 967? It's amazing that I could not try any overclocking on the CPU. Yet, by adjusting room temperature and airflow, I could get a performance improvement of 80% in aircon rooms and 33% in non-aircon rooms that are exposed to outside temperatures. How did I achieve additional CPU speeds without overclocking the CPU? I did it by having an additional fan on the solder side of the motherboard directly blowing air where the CPU was located. So what this did was cool down the CPU silicon die through the leads through the solder on the solder side of the motherboard. That's brilliant, isn't it? I found that many fans are not of any good. Most of them are weak and useless, especially the computer fans. I also found out that if the manufacturer doesn't mention how much airflow the fan generates, normally it's in CFM, cubic feet per minute, don't buy those fans because they will be absolutely lousy and just a waste of money. In the end, I got a very noisy air blower that focused the airflow onto the CPU itself, and it was very effective even though it was blowing 30 CFM. Brilliant, isn't it? As a result of these experiments, there would be more effective cooling if the solder side of the motherboard had cooling fins sticking out to catch the airflow. These fins could be connected to the ground pins of all the chips. It is even possible for cooling pins to be embedded within the silicon die of the chip and are exposed to the air circulation through the solder side of the motherboard. This is how I managed to achieve 863 ranking on Cinebench R20 by stuffing a Sanyo blower into my laptop to force air onto the solder side of the motherboard. I did this experiment at the air-conditioned Digimod where the temperature was 24 degrees centigrade or 75 degrees Fahrenheit. There are 3 more experiments I would like to carry out. Firstly, I would like to source a more silent fan and a more powerful fan. Secondly, I would like to test this with a desktop PC that has a CPU that allows for overclocking. This is because I want to know whether when I have solder side cooling, would the CPU automatically overclock the PC? And thirdly, the most interesting test I would like to carry out is if I remove the water cooler or air cooler on the component side of the CPU, the motherboard, and just have a strong air blower on the solder side of the CPU, would that work? Would it still allow overclocking or would it get too hot to run further? These are interesting questions that we don't have any answers for right now. So do subscribe so you will know the results of my experiments when I publish the videos.